All right, hey AP Chemistry. So I wanted to make a video to kind of wrap up these notes and unrush what we rushed at the end of these notes. So I'm going to talk about ideal gases and the ideal gas law, and then end this video with density of gases and calculating molar mass and density from there. So at the end of class, I rushed through and made you highlight and a gas behaves more like an ideal gas at higher temperature and lower pressure. Remember high temperature, low pressure. That's going to be a question. It's going to show up. It'll show up on future quizzes, and it'll definitely be on the AP Chem exam. But an ideal gas is one that is small, meaning it occupies no space or very little space. Very, very little space. And has no interactions. If I have a very small gas that does not have any interactions with other gases, it's going to directly obey all of the gas laws. So if I have an ideal gas, it'll work perfectly with pressure and volume, volume and temperature, temperature and pressure. If it is not ideal, then it may go outside and its values may be a little bit different than what you could predict or expect. So make a note for yourself. If ideal follows all gas laws exactly. Now, non-ideal shows up here. Look at, and over here, this means that the PV value, the pressure volume value, should be about the constant. Here's the ideal value is a straight line. Neon and oxygen are like right in there, but CO2 is not. And the only reason why is CO2 is big or bigger than NE and O2, and it deviates because it's more polarizable and it has intermolecular forces, so it has the interactions that we don't want for an ideal gas. So we're going to talk more about this in our next set of notes, but just starting here, an ideal gas is one that works perfectly with all of the gas laws. It follows them exactly. So if I were to increase the pressure, I would decrease the volume, or and so on and so forth. Or if I increase the temperature, I should increase the volume, so on and so forth, in a like manner that we would predict with the calculations. If it wasn't ideal, then it would go off. Okay? All right. So, I skipped a page. That's page 9. Hold on. Got right over here, okay? So, page 8 with ideal gas law. Now, I did skip this because I did make a video on plugging and chugging this equation. But again, you don't have to memorize this equation, and this equation will be given to you on the AP exam or on any quiz or test that we have. But it's PV equals nRT. And what's very important is that pressure is in atmospheres, V is in volume, N is in moles, and T is in Kelvin. Later on, we could see that if I have other units, I could use a different value of R. But remember that the value of R right here is always going to be given to you. R is 0.08206 liters times atmospheres per mole Kelvin. Sometimes you'll see this rounded as 821 liters times atmospheres per mole Kelvin. Does not matter which one you use. They would like you to use the one they give you on the AP exam, but you get the same answer. So this is going to be a plug and chug. And so whenever you're given one guess and you have any of the 2 or 3 values and want to solve for the other, you could plug and chug into PV equals nRT. So let's do an example. I'm going to do sample question number 10 here. And we should get 0.57 moles. It says a sample of hydrogen gas has a volume of 8.56 liters and a temperature of 0 degrees Celsius. Now remember, for temperature, we have to convert that to Kelvin. So plus 273 equals 273 Kelvin. And a pressure of 1.5 atmospheres. Calculate the moles, moles being N. And then we know that R is 0.08206 liters times atmospheres per mole Kelvin. By the way, these are just the units. It's kind of like liters, 8.56 liters. L is a unit. This is a multiple unit value. So you're not doing anything with this L, atmosphere, mole, and Kelvin except writing them in and then showing you how to cross them out. So if I want moles from pressure, volume, and temperature, I could use PV equals nRT. If I rearrange this equation to solve for n moles, I'm going to bring the RT over to the left side. So PV over RT is going to be equal to n. And so all I have to do is plug in my values. P is 1.5 atmospheres, V is 8.56 liters, over R 0.08206 liters times atmospheres per mole Kelvin, times T, which we change that to 273 Kelvin. If I plug all these numbers into a calculator, I should get 0.57, and I just wanted to show you how units cancel out. I have liters on the bottom and atmospheres on the bottom, and on the top, they cancel out. I have Kelvin here and Kelvin there, that cancels out. And then I have per mole on the bottom, which ends up on the top. So I am going to end up with moles, 0.57. Just to kind of show you, I have 1 over mole kind of here. And so if I do 1 over mole, that's just mole. That's just showing you units canceling out. It's nice if you show that on the AP exam, and it's nice if you show that on quizzes and tests, but you're not marked on as long as you have the correct units, which should be 0.57 moles. You could try and do sample question number 11, but remember it gives you STP, which is 1 atmosphere and 273 Kelvin. So I have the pressure and the temperature, and it told you the volume is 1.75 liters. And it wants to know how many moles of N2 are present. So again, I have to solve for N. Okay, so I'm going to jump now to page 9, where I rushed quickly, but I want to talk about the density of gases and plugging and chugging that. Density of a gas is typically reported in grams per liter. And if you remember, density is how many particles in a unit of volume. And our unit of volume is going to be the liter, okay? And so there's a special number here, and this is what we could use if I have STP. At STP, which is standard temperature and pressure, 1 mole of gas will occupy 22.4 liters. So this is a very special number that we could use, this 22.4, and we didn't talk about this in class, but it's right here. If I have 1 mole of oxygen at STP, it's 22.4 liters, and you could prove that using PV equals nRT. PV equals nRT. V is nRT over P. If you plug in chug 1 and a pressure of 1 and a temperature of 273, you're going to get 273 times 0.0821, and that'll be 22.4 liters. If I have 1 mole of hydrogen at STP, it's going to be 22.4 liters. 1 mole of NH3 at STP will be 22.4 liters. So there is a special number for 1 mole of a gas at STP. It'll occupy 22.4 liters. So that's a number that could help us convert between volumes and masses and whatnot. And then if I want to calculate the density of a gas, the density of a gas can change with respect to pressure and temperature. So, and you'll see that if I increase the pressure, I'll increase the density. And that was shown in the very beginning, right? Here's page 1 with density. If I have higher pressure, I have more particles that are colliding, and it's going to be more dense. If I have lower pressure, the particles are more spread out, or less particles in a given space. That gives me low density. So remember that from the beginning of our notes here. Okay? And so now if we have anything to do with calculating the density of a gas, I could use this equation. Density of a gas is P times molar mass over RT. And I could solve for anything else if I have those variables. So let's look at sample question number 12, which I wanted to spend more time doing. It says the density of a gas was measured at 1.5 atmospheres at 27 degrees Celsius and found to be 1.95 grams per liter. So I have the density of the gas, which is 1.95 grams per liter. So I already have this value. And it says the pressure was 1.5 atmospheres and the temperature was 27 degrees Celsius, which remember, Celsius is no good. We got to convert that Celsius into Kelvin. So we add 273 and I get 300 Kelvin. Okay. And it says calculate the molar mass of the gas. And we know that R is 0.08206 liters times atmospheres per mole Kelvin. So all I'm doing is plugging and chugging this information into this equation. Density of the gas is equal to P times mm over RT. Now, I could rearrange this to solve for molar mass. It doesn't matter. I'll do that anyways, but you could just plug in the numbers and then solve for molar mass, but I'm going to rearrange it. So density of gas, I'm going to move the RT up here. Density of the gas times RT divided by P is going to give me the molar mass. So the density of the gas was 1.95 grams per liter. R is, of course, 0.08206 liters times atmospheres per mole Kelvin. T is the temperature in Kelvin, which is 300 Kelvin, all over pressure, which we said was 1.5 atmospheres. And if I do all of this math and I cancel out units, right, my liters cancels out with liters, my atmospheres will cancel out with atmospheres, my Kelvin will cancel out with Kelvin, I'll be left with grams per mole. And so if I do all this math, I should get 32. 1.95 times 0.08206 times 300, and then divided by 1.5, and I get 32 grams per mole, which is what was predicted was my answer. And now, if you had to figure out which gas from a bunch of choices, this would be extra. What if I said A was H2, B was N2, C was O2, and D was F2? How can I figure this out? Well, I'd have to figure out all of the molar masses of these gases, and the correct answer would be O2, which definitely has a molar mass of 32. Okay? All right. So I'm ending this video talking about density of gases. I'm about to make another video on page 10 about gas mixtures and partial pressure. So be on the lookout for that video. And you could definitely use this video to help you with the rest of your gas law calculations and your homework.